This screencast is going to cover the second half of the PowerPoint on transport diffusion, facilitated diffusion, osmosis. We're going to look at this osmosis part here today. So in the previous screencast, we had talked about this membrane and facilitated diffusion, and then facilitated diffusion. So now I want to focus on D and E here, describing and explaining osmosis, these terms hypo, hyper, and isotonic, as well as the water potential and how to calculate it. So we'll skip forward through these slides here and get to this one. We'll start here. Now, since water is a polar molecule, it will not be able to cross membranes readily. So therefore, but water does get into and out of cells. So therefore, water is going to diffuse across a membrane via these things called aquaporins. And so an aquaporin is literally a water hole or a water channel. And so this is a facilitated diffusion, therefore, facilitated diffusion, because in the membrane here you have the protein that is going to be the pore for water. So these are water molecules here, and these water molecules will move through these aquaporins. We'll just show it this way. So over here, these cartoons, again, here's this water channel. This is supposed to be the membrane there. And then these ion channels here, water is now surrounding these ions. These ions are dissolved in the water. So you have water molecules here dissolving the ions. And so as the ions move, the water also moves through. So you have two different ways here that water can get across membranes via these aquaporins as well as other channels. But the important point here is that it's not, the water molecules are not just simply passively diffusing across the membrane here. That's not going to happen. So if this water is moving, if these water molecules are moving this direction, the assumption is then that the concentration of the water molecules over here is higher than the water molecules on this side of the membrane. So this is the lower concentration. Water molecules will be facilitated diffusing across membranes from high concentration to low concentration of the water molecules. So this facilitated diffusion of water is called osmosis. So the facilitated diffusion of water molecules is called osmosis. This is a working definition of osmosis until we change it, which we're not going to. Right, so let's talk about this concentration of water here, right? We have to know where the concentration of water is higher and where the concentration of water is lower, so that we can then predict which way the water is going to diffuse. We have to talk about a couple things here, this concept of solutions and concentrations, right? So a solution, again, from chemistry, is defined as some sort of solute per solvent. And the concentration is just this. It's the number of molecules or substances per volume of solvent. And in this case, most often the solvent is going to be water. So a concentration, for example, molar concentration is moles of the substance per liter of solution. So concentrations are different than volumes. A concentration is some number of molecules per some set volume of water. An example would be moles of a substance per liter gets you a molar concentration. So these solvents here most of the times are going to be water. Let's move on to these terms down here: hypertonic, hypotonic, isotonic. These terms here, the prefix here, hyper, prefix hypo, and iso. So hyper is higher, hypo is lower, and iso is equal or the same. So the fact that that end these terms in er, higher, means lower, means that we are comparing, right? So these are comparison. We're comparing the concentrations of two different solutions. So hyper, hypo, iso, higher, lower, equal. Of what, though? This is an important point, so pay attention and listen right now, that these terms, hypertonic, hypo, isotonic, the tonic here refers to the solute concentration, the concentration of solutes here, okay? This is very important, that these terms go with the solute concentration, not the water concentration. For example, let's go over to this diagram on the right here and look at this U-shaped tube. Right? Pardon me. So this U-shaped tube right here has a solution inside A, and there's a solution inside B. At the bottom of this tube, very important right here is that there is a membrane that's going to separate solution B from solution A. And this membrane is said to be selectively permeable, meaning that some things will go across, some things will not. So if we come down here, what is this membrane permeable to? And what is this membrane impermeable to? Okay? Well, in this example, if we are trying to show osmosis, if we're trying to demonstrate osmosis, we need to have a membrane that's selectively permeable. If we're trying to demonstrate osmosis, we need to have a membrane that is permeable to water so that the water will move, but that is impermeable to solutes. The membrane has to be impermeable to solutes and has to be permeable to water. So the assumption is that this membrane right here separating solution A from solution B is permeable to water, but impermeable to the solutes. So if we now discuss this, how do we describe this solution A compared with the solution B using these terms right here? So we'd say the solution A is what compared with solution B? Solution B is what compared with solution A. So you can pause this now and sort of predict what the answer is going to be. So here we go. Solution A, if you describe solution A as being hypotonic to B, then you are correct. This is hypotonic because I'm looking at the water. No, I'm looking at the solute concentration. So each of these dots here is assumed to be a solute, right? So this is a solute dissolved in this water, this solvent. So the concentration of these solutes on this side of the membrane is lower, hypo, than compared to this side of the membrane. We could also say that solution B over here is could be also described as being hypertonic to A. So B is hypertonic to A, A is hypotonic to B. Now, we can use this information to then predict which way water will osmose. Well, remember, if the membrane is impermeable to the solutes but permeable to water, where is there higher water potential? Where is there higher water? There's more water on side A than on side B. These solutes are not going to move. They're not going to diffuse. If that membrane was permeable, then the solutes would move from B to A. But we predict that the water should move from A to B. Right? So this is one way for us to know where the water is in higher concentration. The water is in higher concentration where the solutes are in lower concentration. The water is in higher concentration where the solutes are in lower concentration. Let's move on to talking about this water potential thing down here for a second. A potential, and this is where anatomy and physiology people are going to be a little happy here. There's some overlap. So a potential is defined as a difference in concentrations across a membrane. So a difference is defined, a potential is defined as a difference in the concentration of something across a membrane. We use this concept of water potential. This funny looking symbol right here is the Greek letter psi, which stands for water potential. So psi, this water potential, is measuring the difference in the concentration of water on either side of the membrane. Wherever there is, this difference can also be described as a concentration gradient as well. So if we go back to our solutions over here, the solution on side A has more water that's not dissolving the solutes, right? So another concept here is you can start thinking of free water molecules. And by free, I mean not dissolving a solute. Well, if there are fewer solutes, there's fewer things to dissolve over here. That means that there are more free water molecules here, free to then osmose or to move. On this side B over here, there are more solutes, so the same volume of water, pardon me, will be busy, quote unquote, busy dissolving those solutes, and therefore will not be able to osmose or diffuse across the membrane. So we can talk about water potential being high, meaning that there is a high concentration of free water molecules. If a solution is described as having a relatively low water potential, then there's a low concentration of free water molecules. This is a little complex, but it's simple at the same time. If there are high free water molecules, that means that there are very low solutes, right? And if there's low concentration of free water, then that must mean that there's a high solute concentration. Okay? Now, the water potential of a solution, there's a little equation that goes on here. So the water potential of any solution is equal to the pressure potential plus any sort of solute potential. For right now, these pressure potentials are going to have a positive value, and solute potentials are going to have a negative value. We can assume that let's assume for now that the pressure potentials are 0. Well, these negative solute potentials are directly related to how many solutes are in the concentration or in the solution there. So if I wanted to determine the water potential, let me back up a second, and they're always going to be negative. So as I add solutes, that's taking away free water molecules. As I add solutes, that's taking away free water molecules. If I'm taking away free water molecules, my water potential is going to go down. Right? So solute potentials, right, are always negative because as I add solute, I take away free water molecules. So, question is, what kind of solution has the highest water potential? What's the highest water potential possible? The answer is 0. Right? Water potential equals 0 is just distilled water. There's no solutes, right? No solutes. So let's come back to our U-shaped tube. How could I describe solution A on the left here in terms of water potential? How would I describe solution on side B in terms of water potential? I'll pause and let you sort of take a think about that. Well, again, if the water potential is a function of a solute potential, which for right now I'm saying is 0, a pressure potential, which for right now I'm saying is 0, and a solute potential, which is a negative, which is related to how much solute was added, well, I could say, okay, this side A water potential would be 1, 2, 3, 4, 5, 6, and it's a minus 6, so I'm taking away 6 water molecules. But on side B, side B would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This would be a minus 13. So the question is, which side has a higher water potential? Well, the highest water potential you can have is 0. Again, this is the highest you can have. There's nothing more pure than distilled water. So this is the highest you could have. So which of these, A or B, has the higher water potential? Well, side A has the higher water potential. Side B has the lower water potential. -6, this -6 value is closer to 0 than -13 is. So this higher water potential on this side, side A, and the fact that it's hypotonic, these are two ways of describing this same solution. Water will osmose always, 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 or diffuse from a high water potential to a low water potential. Always from a high water potential to a lower water potential. Water will always osmose or diffuse from a hypotonic solution to a hypertonic solution. Okay. These are two ways of describing these solutions here. That is a lot of information. To apply it to situations, right, to add in the pressure potential, here's a slide describing the pressure potential. Right? If you're a plant cell, you're going to have forces that resist movement of water inside of you, right? Because you have a cell wall. Right? So if you're a plant, a fungus, or a bacterium, right, this pressure potential is always going to be a positive value. Solute potential, again, is always just going to be a negative value here. We need to talk a little bit more next class about this whole way to calculate the solute potential as well. So what I need you to do before next class is to practice understanding this and seeing if you understand it here. So go over the math here. Look at this diagram at the top there. Look at this down here. See if this makes sense to you. Why does it make sense? Look at this slide here. Here's some things to do. Right? For each one, in terms of tonicity, practice your U-shaped tube here, A with respect to B, B with respect to A. So practice, you can just write right on the sheet. Here's more. Predict and explain the movement of each one. So which way would water be osmosing, assuming, of course, that this membrane is impermeable to the solute. Here's a diagram. Predict and explain and identify here. So these are putting the cells into a different solution. So the solution around the cell versus on this side of the membrane. Again, remember membranes are separating there. So describe the movement of water, describe the solutions. And then there are some calculations to do, right? And some sketching and labeling. So the expectation is that you have notes that you're doing summarizing this and this slide and this slide and this slide and this slide before you come to class next time. I also handed out a stapled sheet today, which I will post under separate cover on Blackboard that should also be completed. It's a worksheet that has some practice questions as well as graphing on there. Okay. We also set up the lab part A today, and I will post that those class notes under a separate as a separate PowerPoint. Right? Not a screencast, but just the PowerPoint so you can see what we did. Alrighty.